for giving a talk today. So Hongkai will talk about instability of an inverse problem for stationary radiative transport near the diffusion limit. So thanks a lot, Hongkai.
Thank you, Knut. Thank you, Katia, for the invitation, and congratulations to Gonster. So today I'm going to talk about this topic, and this is a joint work with my former postdoc, Yiming Zhong, who is now at Auburn right now at the tenure track. Okay, let's see. Oh, okay. Going too fast. Okay, so this is, I'm sure many of you know this radiative transport equation. This is convection transport term. This is absorption, total absorption, and this is the scattering. Without this scattering, it will be this typical X-ray model for computer tomography. So the U is the particle density at position X in direction V. D is the domain. Omega is the unit sphere in D dimension. Sigma T is a total absorption coefficient. And the kernel here is telling you how the particles scattering from one direction to another direction. Okay. F here is the the photon or the particle goes into the domain, and the domain boundary in the phase space is partitioned into two parts. One is minus is incoming, whereas the normal of the boundary is the direction is from obtuse angle with the outward normal, and plus is outgoing boundary. So that's the setup, mathematical equation. Please, I know Zoom is sometimes a little bit difficult to get interaction, but if there's any question, please stop me and we can talk that for sure.
I have a question.
Yes.
The gradient in the previous slide, and what variables is it?
In X.
In X, okay.
In X, yes. V is the phase space, yeah. Gradient is in X, yeah. Of course, when we're talking about real application, we are basically interested in some of these parameters, which has physical or application relevance, which is absorption or the scattering. Here we assume the kernel function actually in our future discussion is kernel function is even easier. But in general, we can think of the kernel function is dependent location. And also this is telling you the probability of one particle in one direction, how likely it is going to the other direction. This is also the absorption does not depend on the direction, only location, depend on the location. And the inverse problem is basically you can send in particles in any way you want. Basically, the incoming particle density at boundary point X in direction V, inward direction V, and you give such a source at the boundary, so you measure what's coming out of the boundary, and you want to, through this relation, to infer these coefficients. Okay, that's typical inverse problem. Through boundary measurement, you want to know what's the interesting parameters inside the domain. So, of course, it has been studied extensively, and in theory, especially one proof stability, instability, existence, all these things. Angular resolved data make the inverse problem easier because you have ballistic part like X-ray transform you can use those most singular part. So I found a very interesting phenomenon when I say.
Still not sure about that.
When I say Siri, my phone think of I'm calling Siri, so it's trying to respond to me. Okay, but in practice, angular resolved data is usually either difficult to get. You have to get particles in different directions. You have very good measurement, and also usually that's does not have enough signal to noise ratio because the particle you collect in particular direction is usually quite small. So in practice, most of the time is more realistically you got angular average the data. So which means at each point you just get the density. You integrate against the direction, you get the total photon at that location rather than photon at location in particular direction. Okay, so there are, as I said, a lot of study about stability or instability depends on which you're more emphasized. They usually look the same, but when it's very bad stability, usually you're talking about unstable. So I don't distinguish in the later about stability and instability. But I'm trying to say the stability in this case or instability is quite strong in this diffusion limited case and how the transition is. So for stability for angular resolved data has been studied. This is far from complete, but has been studied. Stability for angular average data also has been studied, but it's like linearization for small perturbation. Stability for angular resolved data near diffusion limit has been studied by Lively and Gonzar here. So, but this is for angular resolved data. So in our study, we consider, well, again, we try to emphasize instability for angular average the measurement, okay, and also during the diffusion limit. So in a sense, we know the stability or instability, whatever you call it, it's transition from Holder type, which you lose a few derivatives when you're talking about X-ray, only the transport part, to logarithmic type when the mean free path becomes very small. That's become diffusion equation, and we know for Schrodinger equation for the potential or EIT problem, this is logarithmic type, so which is you can call it instability. And characterize especially the, I don't know why, the balance between. So it's basically the transition is a balance between the transport and diffusion, which one is more dominant. But in our result also shows it depends on the perturbation. Depends on, it's not, you don't have absolute criteria, but it also depends on the perturbation size or the noise size, whatever. So we will see the result. But the framework, although it's much more technical for this problem, but follow the main approach, the methodology by Mendashi for EIT problem, which is just a Schrodinger equation, or in 2001. But I think this approach is definitely I think it's very interesting. Give another perspective. Instead, it's very constructive. So basically, all this instability, you want to give a sharp estimate or sharp kind of example, because you only need to show one example where it has this kind of bad stability or instability. So all these things need to be constructive. So you need to construct, but you only need construct in one setup, and that is good enough to show that the general bound should be of that type. So again, we only need to find one example where the stability is really of logarithm type, or instability is of that type. So here we interested in, say, I give you, suppose I know the scattering coefficients. I just want to recover the absorption coefficient. Even that, we will have that type of stability or instability estimate. Okay, so this is, and also our scattering is simplified. Again, so we only need to construct one example. So we make things as a, if it's an example, if the model is too complicated, then it's very difficult to construct an example. So here we simplify as much as we can, but not to simplify to the extent that the instability disappears. So here we simplify the scattering time. A scattering kernel is just isotropic. Okay, you have equal probability to go any directions. So it's become, the right size becomes just the total density of the photon at that point. And the left-hand side is of this limit. Now of this form, the epsilon is basically the one of the mean free pass. Epsilon is a mean free pass. And then we try to see when we recover sigma A, there could be what kind of instability. Okay, so this is the setup, simplified setup for our constructive approach. And our measurement, okay, is the averaged one, which is, since we know what's going in, we know is a total, so this is a total flux at the boundary. But since we know the incoming flux, of course, we only need to measure this in order to know the total flux. Okay, so this is what our setup. Yeah, we know if sigma s is equal to 0, there's no scattering. And then this is Radian transform, and we know this is Holder type instability. As epsilon goes to 0, we also know the RTE approaches diffusion limit. So that's become EIT type of problem, Calderon problem. And it has logarithmic stability. So how it goes from here to there. Okay, so this is, we try to investigate. Okay, so I know there's notation wise, so the things become a little bit more messy and technical, but I try to summarize the main points. I think the detail you can definitely find it in the paper, but for notation wise, for rigorous, I still keep some of the messy notation. So again, we try to construct a specific example to show this type of instability. So our domain is a ball. Simplify the geometry. K is a compact set. So in this case, it's a smaller ball with the radius strictly smaller than 1. So basically, you want to recover interior absorption, and this interior is strictly interior. That's R0. So my sigma A, the absorption coefficient, only supported in here, and has Q derivatives in this space. So this Q is parameter. It's really tell you how rich your absorption coefficient space are. Right? The smaller the Q means the wider the absorption can be, the larger the space is. So we're talking about mismatching of two spaces. So this is the space where our unknown states. Okay, so this is space our unknown states. So the main thing is it has compact support inside and also has this regularity. Then our result shows basically say this is basically the difference in the measurement. This is perturbation in two absorption coefficient, two media, two tissue. Okay, they are infinity norm is separated apart by theta. Okay, this is the perturbation or the difference between two media. Of course, they are all kind of close to a reference media. Okay, in infinity norm with this theta, the same theta here, and they're close to this in CQ norm by this beta. Okay, so all this will parameter will come into our estimate, but roughly, I think the most important thing is this is the perturbation or the difference between two medias, and this is the difference of the measurement when you consider it's a map from HS to H minus S. And well, when we're talking about stability, choosing the S is not essential here, especially this condition. The D is a dimension. Okay, D is the space dimension. So this is a technical requirement when we need to go through some of the proof. I will, if I remember, I'll mention that it's probably near the end of the talk, but this is technical assumption. But so when you measure this from S to minus S, we can show, so the crucial thing is how the right-hand side, the perturbation is theta, how the right-hand side depends on theta. Well, that dependence is really, it's a little bit complicated because it will show where diffusion, where is the holder type. So that is where this function comes from. Okay, so I don't know whether you can absorb this or not, but in order to find this explicit in theta, okay, you have to put these things into here, the T, and solve for this omega. Okay, so this is tell you how the perturbation omega depends on the perturbation theta, but it's not a simple form. You have to go through solving this equation. Well, it's complicated enough, but you can simplify that to show when the diffusion is. This is basically the term of the diffusion. This is the terms of the transport. So it's really balance of these two terms. Of course, there's this term too. The tau is kind of similar. It's a polynomial. This is log. So it's balance of these two determines whether you're in transport domain region or you are in diffusion region. Okay, so for example, just make things a little bit simpler. Just basically make this term looks like this term. So then you just have two simple balance. So you basically, you choose S to be this particular number. So then they're only, this becomes that. So you have this balance of this with this. You'll find, so this is interesting, I think, is result is, it's not how small epsilon is. It's how small epsilon is with respect to the perturbation. If it's small, okay, so this theta is my perturbation. If it's this small, then diffusion dominant. And then you see, although these two absorption coefficient did separated more than theta, the measurement is, the difference in the measurement is less than this, which is exponentially small with respect to this. And when eta epsilon is still small, but is not small in terms of the perturbation, then you got a holder type. Okay. So that's the two regime. And I think the one important message is the how small epsilon is or not only depend, there's no absolute things, it depends on the perturbation size too. Okay, so given I think I'm probably behind the schedule, this is some basic fact about some basic fact result for the transport problem in general. Okay, but I think want to say introduce this adjoint RTE because in our proof we'll need this. Rough saying the adjoint things, then you're talking about the boundary integral things. Okay, domain is here, the boundary of the domain, but you integrate against the whole omega because we're talking about the full flux through the boundary. So okay, so it tells you there's some dual relation between between this boundary measurement source here for this adjoint problem and the boundary source for the original problem. So it's really the dual things from here. And this is the solution to the dual problem. U is a solution corresponding to the original problem with this source. Okay, so this is not linearized version. So you will see where basically say we want to see the U0 means I don't have absorption, only transport. Then we want to see when there is sigma A, when sigma A is now 0, what's the difference between U with this absorption, non-zero absorption coefficient, the difference between that solution to the solution where there's no absorption, right? That's basically the information we have at the boundary, all we have. Okay, so since this is not linearized version, you see these things depends on the solution to the transport equation without absorption, okay? Without absorption. So I think also the difficulty is you need to find, because the constructive, you need to have a good approximation for this one, transport in a ball. Okay, that's why you also want to make geometry simple, because otherwise you can see very little about this, then it's even harder to control this. Okay, so this is something we want to study, especially the boundary, right? This is, I said, that the boundaries of this phi is what we measure, we can detect. So you really, everything is about how this map compress things. If you're talking about stability, most of the time is because your forward operator is smoothing, you're compressing. So your rich data space here is the sigma A, it's quite rich. But then when you, through this transport mapping, when you map to the boundary, you want to see how much compression it gives, okay? Especially basically you want to see how high frequency is damped, how fast it is damped. So the boundary term has two, so it's very interesting. So that's basically the two terms come from, the two balances come from. One, if you have any G, okay, so you want to see what is this operator doing in F, so you're doing against some, so you want to see how it's doing on a test function. In S, we're trying to see what the operator from H minus S to HS to H minus S. So this is a way to characterize that. And it has two terms. Okay. These two are equivalent. One is using adjoint, one is using original, but we're using either of them, depends on different scenario, but they're conveying the same message. This action has two terms you have to control. One is the average of the solution, you average out in the angles, so these things. And G is the harmonic attention for this G, okay? So you can do a harmonic extension here. Okay. And you will see this term is relatively easy. And here is where you really need to know about phi. Okay? You need to know about phi because it's here. Here is, okay, you will see why we use this. Okay. But you can also, this term can be equivalently written out in terms of, if you remember, this is the solution to the hadron equation. Okay. And this phi tilde is W minus W0, which is the hadron equation without diffusion. And in this case, yeah, that's right. So one of the complications, of course, is if you're talking about Laplace equation, then basically the Fourier mode on the unit sphere or all the things is automatically is an orthonormal basis on if I'm assuming I measure on the ball, so that's a good sort of basis. So we only have to focus on how each of this, if my incoming source is this spherical harmonics, and how it is mapped to the outgoing measurement. Okay. The thing is, for each m, there is j harmonics, and the number is here. Okay, those are technical, but this is useful needed to do the estimate. Like sometimes why you see there's some d comes into the play is coming from here, the involvement. Okay, so here is the key estimate. It's basically saying if my incoming source, illumination source, is spherical harmonics on the sphere on the boundary, which is a sphere, it is mapped. Okay, then you can expand its a measurement. It's outward going this flux also in this expanded in this basis, and you can see the compression, basically how high frequency is damped. The frequency is L, okay, the maximum M and the N, okay, the frequency is L. So it's coming from here. If you still remember, this R0 is the compact support where the sigma A stays in. So that's because you're inner, you want to, the absorption is supported in a smaller ball. This is R0. That's diffusion part. And this is coming from the absorption. Okay. Sorry, transport term. So this is how compression. So here the compression is really strong. That's why you have logarithmic. Here is not. It's related to the power of L, and it depends on epsilon. Okay, so there are many things play a role. So it's balance of these two. Okay. Again, I give a sketch of the proof. It's a little bit messy and technical, but again, I try to emphasize when we this term, this quantity at the boundary, this is on the sphere, has two parts. One is this, okay? One is this, okay? As I said, there are two terms. Because we're doing nonlinear, so this term has to be fully there. So the first term is relatively easy. So in the sense, it's totally due to the harmonic. You know everything about the harmonic extension of the spherical harmonics. So it's going like this. And that's where the R to the R0 to the L's power comes. Okay. That's basically the simple story of this is this. Okay. yeah, so this is what we want to show. So, okay, so yeah, I just, this is nothing, it is just to remind you what is this term is. This is harmonics extension of a harmonic function on the ball. And then UMJ is nothing, is a solution to the original, the non-zero absorption coefficient, original RTE with non-zero absorption coefficient with F equal to the harmonic, the boundary source equal to the harmonic function. 0 is the solution to the RTG with the zero coefficient, but source is still this one. And this terms here is satisfy this, okay? The difference between the one and this one, okay? Non-zero absorption coefficient and the zero absorption coefficient. So due to the dual relation, we can switch this to, okay, basically. So then we only have to do one case is when n is bigger or equal than m, we want to show the first term is compressed or decays with L. Well, yeah, this is n here. So equal to that. And these things, the second term here is decays like this with n. Oh, well, this is not n. N has no control, epsilon, but here has n. So as I said, the first term control is relatively easy. You write it out the integral form for the averaged solution, averaged in the angle space, and you can explicitly write out the kernel of this kappa 1, kappa 2, and you can give some estimate bound on this. Okay. But the crucial thing is again, as I said, so this you're not afraid of. Okay, it's because it's bounded from here. Okay, it's these terms that give you these things. Okay. You know, you have this particular harmonic extension, it's explicit one. So now, oops. It's the second term. Okay, it involved this, you have to control this. So you want to show this. So here, the difference satisfies this equation, and you basically need to know what these terms look like because that's the source, and this source through the transport is affecting the phi everywhere. So you really have to control phi through control of this. These things, remember, is the simplest transport equation, not simplest, but almost simplest because we try to pick it simple enough. You can have a good, more explicit expression of this. So this is the solution to the transport equation without absorption. And in a spherical domain, and with the boundary source is spherical harmonic. Okay. So, and then you can decompose into two terms. One is the boundary terms. You don't feel it because sigma A, remember, yeah, there's let me see. Sorry, yeah. I'm using this as the thing, so then my finger touch the mouse and then it goes through different pages and I lost the things. Okay, so but this one, interior one, you can use diffusion limit to bound it. Basically, that's the main idea, but there's a lot of calculation you need to do, and it's quite messy. Okay, so I hope that's the things. Yeah, so still to control this. But the main things you have to control this. Okay. And this is, that's, I said, you need to roughly solve this diffusion equation to give you this concrete control on this, and you will have this. Okay. Okay, so I think it's too technical, but the basic things is these two terms, you have to bound it. This term, which is corresponding, this is almost the same as Machuda proves this stability result for the EIT problem. That's the first term. This is the second term, is unique to this problem. Okay, you have to do, and then you use diffusion limit to do that. Okay, now I think that's the most problem specific estimate you have. Once you have that, then there's also a kind of standard, quite in some sense, it's standard machinery to do things, but still depends on the previous result. This standard machinery could be quite computationally messy. So here it's coming from here. The basic idea is you need to describe how big the unknown space is and how small the measurement space is. And through this relation, you can see how you can find the maximum instability or the sharp stability conditions. So one way to describe a set is small is through the delta net. So basically, how many numbers you need to have in the set such that this set provides a delta net for this space. Okay, so basically every element in here is delta close to one of the element here. So why this? You want to know how small this is. And you want to see what something is big. So this is, we want to see our measurement space is small. We have a small delta net in terms of the delta, depending on the delta, and how big the sigma theta distinguishable set. So basically, you can find how many elements in this set such that they're all theta away from each other. Then there is a little bit of modification, but this is really something people, Kolmogorov has already shown that this set is, okay, what set? It's depends on infinity norm of F, depends on the CQ norm of F. Then using this, you can find the mu is a constant. Mu is a constant. Then you know how rich this set is. Okay. So there are at least this many elements. Again, it's constructive by using small support things, doing scaling. You can find this many elements in this set, such it's total. They're theta away from each other, and the number has to be bigger than this. Okay, depending on the dimension. This is a constant. Depends on regularity, beta here. Depends on the maximum norm theta, depend on D and Q. And here you see the smoother the Q is, the smaller the number is. Okay, the smaller Q is, this is the bigger this thing is. Okay, in terms of distance. So this is a well-known result. Now we need to study how small the measurement space is. So we have to give a good characterization of where our measurement, the set, about the set which the measurement stays, or the space where the measurement stays. Remember, we're talking about thinking about this is a mapping from HS to H minus S. So naturally, you know, the norm. If you tell me this, how each spherical harmonics is mapped to the measurement space, this coefficient, again, expanded in this basis. If you know this coefficient, then you know this norm is bounded by this, okay? This coming from here, this coming from here, so, okay, that's where this thing comes from. But most important thing is you need to know how these things depends on M and MJ and K. And we have it, we have the estimate of that. If you remember, that's exactly the key estimate is about, is to estimate how this depends on M and N. Okay, so, and this is relate. So if this norm, okay, operated norm, is bounded by something like this. Okay, from here, you can derive this. Okay. And now, this is something related to what we showed, the estimate. This is the reason why we want to transform this norm into this bounded in this way. So now we know our measurement live in this space, okay, where this is less infinity. Okay. Okay, you remember this is very, you don't remember exactly, but you probably see similarity between this things and our estimate. Okay, then we can say, okay, so this is this, okay, it's bounded by this because this is coming from the specific problem, using this space. Depends on our key estimate there, which depend on the problem. Okay, now we try to see basically how big this space is. We want to say this space is small. Okay, so our parameter space definitely is in here. Okay, here we only need the infinity norm is bounded by R. Okay, then we know this gamma maps these things into XS. Here we need this. Okay, this is because there's some infinite series you have to estimate in order to make it finite, so that the tail you don't have to care. You need this. Okay, but the whole result is roughly saying the small the measurement space, okay, where gamma map this to is small. Okay. So gamma map this into XS, and we know XS is this small. At most it's big, or it's this small. Now everything else is a simple pigeonhole principle. You're mapping a set of points, was a set of elements. If their number is bigger than the pigeonhole you have, then two has to share one. So here is, and also that distinguishable set, sigma distinguishable set, once this set is number of elements in this is bigger than the delta net in the measurement space, then there must be two elements here. They're sigma apart, but their measurements is delta close. Okay, so that's basically this. And you can see the balance is really this. Okay, that's where that weird equation comes from. This is coming from your perturbation, how much the sigma is the sigma distinguishable set, how far apart away to coefficients are, two parameters are, and this is how close, delta is how close the delta net, okay, the delta net. Okay, so that's basically this logic. And you just solve this equation, you recover the beginning, the statement, the corollary is when epsilon is smaller than this, okay? And you solve this, you know, delta depends on sigma, theta. Okay, so the perturbation. So basically, say if epsilon, the mean free path is small, quote small, determined by some function of the perturbation. It's not strict, you know, absolute small. It's small compared to this, and you have this. And if it's big, then you have this. Okay, so that's the diffusion region. That's transport region. So just to final remarks, so basically we use concrete example, constructed examples. Not everything explicit, but try to simplify things as much as possible so you can do this estimate or expression more completely, more explicitly, so they can do all this estimation, and we can show that your stability result cannot pass this. Okay, this is the definitely when they meet that, you know, the stability and estimate is sharp. And also the angular result data do not provide better stability near diffusion limit. I think the approach, again, is we follow the Machida's approach. I think it's very interesting. I also think that's in practice, it's really tells you cannot create something from nothing. So if you know your measurement space is small, you put a lot of resolution in your inverse problem and you pray, eventually what you get is still the artifact. It's not really what the data or the model can give you. It's, well, you can say you have prior knowledge, that's true, that's definitely true. And that means you reduced your unknown space, the dimensional space. Nothing is magic, so if you want to cover something, you have to have enough data, you have to have enough information. So there's nothing surprising here. It's really, you know, this kind of basic information content or theory argument shows why stability or instability result in inverse problem is important. Okay, so I think that's all I want to talk about, except thank you for listening.
Great. Thanks so much, Hongkai, for guiding us through this problem. Very interesting talk. So now the floor is open for questions. If you have questions, please unmute yourself and ask Hongkai.
Hi, this is Margaret. Hongkai, that was a very nice talk. Yeah, I was just wondering, you had the terms balanced in a certain way with epsilon and 1 over epsilon. Would it even make sense to balance them in a different way? Would something different happen?
That's definitely, it changes, yes. Yeah, it's definitely related to this scaling things, but I think eventually the balance will be similar. Maybe the power become even more complicated, but I do not think that the nature changes because that's just polynomial differences. Here is exponential and polynomial. So I think that maybe the expression is different, but I don't think the result or the conclusion is different.
Yeah, thanks. I think it's really wonderful how you're able to sort of balance these different effects in this equation. This is great.
Yeah, I think so. I think the key things again, you have to choose the problem because it has to be quite constructive. You have to choose the problem you can handle. At the same time, it's not remove the essential property of the problem. So yeah, that's basically yeah. You have to balance this too. Yeah.
Any other questions for Hongkai?
I don't know if you mentioned this earlier in the talk, but do you know if there's any results for having angularly averaged sources and measurements?
I think our is all angular. Our sources do not depend on angular either. If you think our sources is this spherical harmonic, so it does no dependence on the angular, right? F is equal to y and j. So this is angular independent source, angular independent measurement.
Okay, I didn't realize that.
Oh, sorry. Yeah, I probably didn't emphasize too much our F. That also simplified the things. If you have angle dependent things, the solution to U0 is more complicated for sure. But here, and also interesting because, yeah, because it's angular independent. So, there's technical things, there's a lot of technical things. Is one thing is it only depends on the flux on the boundary. That also makes things a little bit easier. Otherwise, I think we have more difficult control, more difficult construction or understanding or expression or estimate on this source.
Yeah, that's very nice.
Thank you.
Hi, Hongkai. This is Arnold.
All right. Hi, Arnold. Long time
Hi,
no
it's been a long time. I hope you're doing well. I have a quick question. So it's very nice, and I like the explicit balance between the kind of the ballistic and the diffusion. Do you think, I'm asking to speculate here, if you had a very anisotropic source, could that change the balance of these two in your estimates and things like that? Is there any, so I guess what I'm asking is, if you can control the source, can you effectively change the balance between these two kind of effects?
Very good question. Let me think.
I know that's precisely not your analysis, but
Yes. So I definitely think so, because, well, yes or no, because as I mentioned in the reference, Lai, Li, and Qing, they proved that with angular resolution, you still have this kind of phenomenon.
Mm-hmm.
So it doesn't matter, but in their proof, of course, they don't have this balance because they just throw away somehow the high order term. So here we need to really suddenly balance. We get a very explicit formula. There is basically saying when the transport term can. That's a good question. Actually, I don't know whether their result can say what, because they just basically throw the transport term away.
Yeah, intuitively, right? People that like the practitioners have thought that if you measure the albedo operator, there's a difference in the spatial dependence of that may have more transport versus more diffusion or something.
Yes. So it's very interesting. So then it's really maybe you need this. You use a better basis to make to understand this this operation. These things. So basically, you cannot just stay here. You cannot using spherical harmonic as the basis to do this. You need to including the space in there. So that's, I can see definitely it's you can imagine, right? This is this coefficient where I said the 4 tuples will be not 4, it could be 6 or 8. That become, then you really have to understand in the angular space how it's compressing. Right here, I just we will average the angular, how much spatial resolution compressing. But there you have to understand how much compression you have in the angular. But if you're very anisotropic, I do not see. But there's a balance, right? There's still compression in space, but there's not enough. So how you balance it, I have no idea. But the key things, you not only have 4 indices, you have many indices. You have to really study everything is in the phase space. And you don't have this nice harmonic extension to construct the solution to
Right.
It's becoming, I think, messier. But I totally understand your question. I think it's very nice. It will be someone can see the balance in a much more subtle or complicated when you have not just simple averaging in angles, but there are preserve some singularities. Yes.
Okay, thank you.
But it's a very good question, but it's much harder, I think.
Yeah, I understand. That's if you figure it out, can you email me, please?
Oh yeah, maybe. Just be patient.
Yes, of course.
Any other questions for Hongkai? Otherwise, let's thanking once again for a very nice talk, very nice tools for a challenging problem. So thanks a lot, Hongkai, and thanks a lot for everyone for coming to our talk today.
Yeah, thank you all.